Okay, now welcome back. So now we're going to look at snubbers. What is a snubber? A snubber is just a device that is used to suppress or to snub, okay, voltage transient. So you should know that once there is switching, right, from what we did in Module 1, there's always a transient. Right, so we need to look for a way of suppressing those transients. This transient could be as a result of change in current with time when you switch on your transistor or any of the semiconductor devices. And also transient can be as a result of a change in voltage with time when you switch off your transistor or your switch. And also, we can also have a change in voltage with time, dividity, transient when the supply switches on, immediately. Okay. So we're going to look at how we can protect our semiconductor devices from this. The IDT, from this transient, all right, due to the rate of change of current with time as we switch on and off, and also due to the rate of change of voltage with time. So now let's start with the IDT protection. So in this case, we use inductor in series with a switch. Okay. So now we have this switch. We need to protect this switch from the IDT, the rate of change of current with time. We need to suppress the transient of a current. Okay, and for us to do that, we put an inductor. Remember that inductor builds current. Okay. So what I'm going to do now, once I put an inductor here, as you have your Vs, and once this switches on, all right, this inductor will start building up current, and then the voltage across that inductor will depend now on the rate at which the current is being built up, right? So this will be the voltage across the inductor. That is VL is L the IDT. Okay. Now, so that voltage, the voltage across here, which I'm going to take now as the total voltage, assuming that this is very small. All right, then I'll have that VL or VS. If I take this equals to VS, okay, especially when this is small, or when this, if this is shorted like that, the voltage across here equals the voltage across that. So VS equals to VL, so which will be equal to L the IDT. Okay. So that the IDT will now be Vs over L equals the IDT. So you can use this to calculate the inductance of this inductor. Because if you know the source voltage and you know the IDT, you can calculate the inductance. Just like this question here, it's an example. You are given the IDT as 75 amps per over microseconds, and Vs is 250 volts. We are asked to calculate Ls. So Ls will now be Vs over the IDT, which will give you 3.2 microhenry. Did you get that? All right, so now let's also check how we can protect our system from our switch from the VDT. So how do we protect this switch to snub, for us to snub the transient? Okay. Now the voltage transient. So we're going to have a snubber that is made up of a resistor, which is in series with the capacitor, and you connect that in parallel with that switch or with that semiconductor devices. All right, so now we want to protect this transistor against transient voltage. All right, so for us to do that, we are going to connect a snubber, which is an RC circuit, in parallel with the switch. Okay, so why do we need to put this? Remember that because we are protecting this against the VDT. Now, once you switch this off, once this is off, we want this to build up voltage. Okay, so this will build up voltage, from 0. All right, instead of that voltage destroying our our switch, so this builds up voltage until it gets to peak value Vs. Where this is fully open, the voltage across here, because the voltage across that, assuming this is small. Okay, so now, have that the VDT can be derived, okay, to be the same thing as 0.632 Vs over tau over time, okay, our time constant, and then which is 0.632 Vs. Yt is the product of this and that, RSCS. Okay, the snubber resistance multiplied by the capacitance of the snubber. Okay, and this RS, remember that this is open. When this is open, so current is supposed to flow like that. Yeah, so the current flowing, or the resistance RS, will be the same thing as Vs divided by that current flowing through here. All right. So which is a Vs over ITD. Now, and if we look at this graph, this is our time constant here, which is RSCS. Okay. Now, the point at which it will get to, for you to get that exact time constant, is what will that voltage is what we got here. So if I take that, all right, that is this, the same 0.632 Vs, right? Now it builds up, the voltage builds up until it gets to the maximum value. All right, and if you want to calculate the energy, you just divide, the power, you divide energy by time, which is the same thing as energy is half CV squared, divided by time. And we know that 1 over T is frequency. So frequency, we can still write 1 over this T as frequency, switching frequency, the frequency at which this turns on and off, on and off. So you have that power is half CV squared multiplied by the frequency. Okay, let's look at this question. Let's look at this, this example. So here you have a RC snubber that protects a device against the VDT. So if calculate R, if ITD is 10 amps and the source voltage Vs is 240, and the calculate also the VDT if CS, the snubber capacitance, is 0.1 microfarad, and calculate the power if switching frequency is 1 kilohertz. So RS is Vs over ITD, which is 240 over 10, giving you 24 ohms, and the VDT is 0.632 Vs over RSCS. Okay, just substitute, you will get the VDT to be 63.2 volts per microseconds. Now, also the power is half CV squared times switching frequency. So that gives you half 0.5 times 0.1 micro times 240 squared multiplied by 1000. That gives you 2.88 watts. Okay. So did you get that? Okay. So please just remember that when RL is given to you, right? When this R of the load is given to you, then you can also put it in the equation so that you have the VDT is 0.632 multiplied by RL VS over CS over ROS plus RL all squared. Okay? If RL is given to you. Right? If it is not, then you take that as RL as you take it out of the equation. Okay, did you get that? All right, thank you.